In class on Friday, October 6th, we looked at 2.3 notes and wrapping up some key ideas about the slope function graphs. So just really quickly, let's take a look at the bottom of page 1, number 4, based on the function graph and its derivative graph. We drew the derivative graph, we plotted the zeros, the horizontal tangents occur at these x values, so we plotted slope values of 0. Then we looked for the points in between the zero tangent, horizontal tangents, and said where is the slope going to be the greatest negative rate of change or the greatest positive rate of change on that interval between the two zeros. We plotted, we're just estimating what these values are. Okay, I should do those in red. Those are my slope values. So if we go from a zero slope to small negative, the biggest negative possible at this blue dot, then we're still negative, the slope is still negative, but getting less negative, so heading towards 0. So if you think about the derivative graph, going from 0 to the most negative, back to 0, going from 0 to the most positive, and back to 0. What are the slopes doing to either side of those of this red tangent or red derivative graph? The slopes on the left here are positive. The curve is increasing. So I'm just going to make some positive slopes and have them come down to that 0 point. Positive big here, getting smaller, still positive. Smaller, still positive, headed to 0. The graph should be smooth because this is a polynomial. All right, beyond this farthest horizontal tangent to the right, we have small negative slopes, bigger negative slopes, bigger negative slopes. So we're going to head downhill. Okay, so this is my derivative graph, my f prime of x graph. Soon we will find an equation for that f prime of x graph. Right now, we just want the general shape and behavior of the graph, that is the derivative of the function f of x. Okay, let's answer these 4 questions, making connections. When the derivative function, that is, when is f prime of x, when that's positive, what is my function graph doing? So if the derivative is positive, here we have positive, my function is increasing. So when the derivative is positive, it means the slope is positive, it means my function is increasing. When the derivative is negative, here we have negative derivative. What's happening on my function? My function is decreasing. Okay, when the derivative function, f prime of x, changes sign from either positive to negative or from negative to positive, what's happening on our graph? So here at this point, when x is 1, my slope derivative, the red graph, is changing from positive to 0 to negative. What's happening on my function at that point? We actually get a maximum. So when my derivative changes from positive to negative, we have a maximum. All right. We also call these points in general turning points. So let me move this. So I'm going to say we have a maximum turning point. When our slope graph changes from negative to positive. So look here at positive 2.5. My slope is negative, then 0, then positive. What's my function doing? The slopes are decreasing, the slopes are increasing. My function's changing from decreasing to increasing. Sorry, I might have said that incorrectly. My function is decreasing, my function is increasing. Just clarifying. So the slopes are decreasing, slopes are increasing. What's happening right here at this point? That is a minimum turning point. Okay, next, when the derivative function, f prime of x, has a turning point. Okay, we just learned about turning points on our function, but now we want to look at turning points on our derivative. So point A and point B are turning points on the slope function, f prime of x. What's happening on the graph of f of x at that point? Well, those points correspond to these blue points that I put on my graph. What's happening on the function? Those points are the place where my function changes from concave down to concave up, or concave up to concave down. Okay, so these are locations, or I could just call them points. Locations where f of x changes concavity. They're also called inflection points. So we have not heard that word or that vocabulary before, inflection points, but those are the points, the blue points on my graph, where the function is changing from concave down to concave up, or concave up to concave down. Okay, I'm just going to show you the answers to the slope graphs for the rest of the packet on page 2, number 6, A, B, C, and D. So you can pause the video and take a look at these. On page 4, oh, I lied, not page 2. This is on page 4 in that packet. The red graph is the derivative graph. And I've put some other notes on this page. Notice the red zeros on the x-axis. Those are zeros of our slope function. Those happen because the function f of x has horizontal tangents at those places. Those horizontal tangents happen to be locations of turning points on my function. So the first two bullet points here are really talking about the same location on f of x. Okay, the green points. Those places on the graph of f represent the place where the function is changing from concave up or concave down. They also represent the maximum or greatest rates of change. So the greatest positive or negative rates of change correspond to places where the function changes concavity. All right, finally, those places of, oh, and we also just learned that those are points of inflection. Okay. If you look where the points of inflection land on the derivative, or correspond to on the derivative, the red graph, those are turning points. So points of inflection on the function are turning points on f prime of x. Okay, and then the last 8 graphs, some of them are repeats from homework, but here are the answers to the last 8 derivative graphs. So they're drawn there in purple. Okay, today in class, one of the things we only did a little bit on section 2.4, and that was to look at the idea of other notation. So we've learned that f prime of x represents the first derivative. Another notation for first derivative is this dy dx. And we say it just like that, dy dx. But what it really means, I mean, it kind of looks like change in y over change in x. That's what we're really talking about. But this is just slope of a secant. Okay, this is slope of a secant, or average rate of change. But this, remember, is our first derivative. So we're looking at very, very small differences in y values and very, very small differences in x values. Sort of like when we look at y1 of 3.001 minus y1 of 2.999. We're making our x values very close together. Oops. Okay, so very, very small differences in x and y. Okay, we talk about dy dx as the derivative of y with respect to x, because y is the dependent variable and x is the independent variable. Okay. All right, I want to show you how we are going to find the slope function as a function. So we have looked at f prime of a, the slope at a particular point, right? The derivative at x equals a. But now what we'd like to do is, thinking about some of those graphs, could I come up with an equation for each one of these purple graphs? Well, they look like functions I would know how to write. I know how to write the equation of a parabola. Okay, so we're going to look at how to find the slope function given f of x. All right, in this video, I'm just going to write down the definition of derivative at a point, which we already looked at. And the definition of derivative that's going to get us a function. Not just one value, a function. Okay, so at a point, f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. That is the derivative at a point. This results in a single value, a single slope value on f of x at a f of a. Okay, we're going to use this in the next video that I'm going to post, not this one, the next one. We're going to look at f prime of x. Okay, well, how's it going to be different? We're not going to plug in a specific value for x like we did over here. We plugged in a. We're going to leave it in terms of x. So we have the limit of f of x plus h minus the limit of f of x all over h. This will result in a function. What function? The derivative function or the slope function. Okay, so look for another video to come, probably not until Sunday night, and have a super awesome weekend. See you Monday.